So we're Chichester Humanists. I'm Andrew Edmondson, the coordinator. And we provide activities for non-religious people in and around Chichester to meet, debate, socialise, though not so much at the moment, and support one another. So we're also a branch of the national charity Humanists UK. Just to remind everybody, this event's being recorded, so if you don't want to be recorded, just mute your microphone and turn off your video. And I think Richard will probably mute everybody when he's speaking, but when we have some questions and answers afterwards, just mute your microphone if you're not speaking to avoid any interference. There's the chat. I've got a chat window open on the right-hand side of mine. You can open the chat if you want to ask questions or make any comments. And you can also adjust the view on Zoom. There's a top right corner. There's an icon called View, and it just changes the way you can see things. I think it just toggles in two different ways. Anyway, I'll introduce our speaker. He's Richard Faragher. I hope I'm saying that correctly.
You're not actually. It's Faragher.
Faragher, right? Okay.
No, don't worry. It's I've had 50 years of it. One more doesn't matter.
Right. He's a professor. Just correct if I'm getting this wrong. He's Professor of Biogerontology at Brighton University, and is past chair of various societies: the British Society for Research on Aging, International Association of Biomedical Gerontology, and the American Aging Association. His primary research interest is the relationship between cellular senescence and organismal aging, and he's received various awards for his research. So over to you, Richard. Let me know if you get any problems, and I'll just sit back and we'll enjoy things.
Well, okay, so hopefully everybody can see that. Although obviously they're University of Brighton slides, I'm not at work, so some of the things that you'll see here are not things that I would normally put in say an undergraduate lecture, because it goes far broader than that. So let's just, as I say, that was the title that I thought you might find interesting. This is largely modelled on talk I gave at New Scientist Live a couple of years ago, although I've incorporated some additional information since then. And so, in essence, this is what I'm going to talk about. What's aging? What is it? What are aging researchers doing and doing about it? How does it work? What's on the horizon? How should we think about it? It's probably a good summary of where we are. And because of who I am and where I work, I thought I would start with some reassuringly bad news, because that's all you ever get about aging. Now, just so you know, about 20% of people or less at the moment can be described as undergoing what we call successful aging. And that has this kind of positive ring, but actually it's a pretty low bar. It means, are you able to get out and about? Do you have any friends? Are you free of most major diseases? All right. And for 8 out of 10 cats, that is not going to be the case when you're old. If we look at things that normally form a kind of salience of coverage of the older population, older people are responsible for about 70% of all items dispensed by the NHS. They make up the overwhelming majority of admissions to hospitals and adult daybed stays, and the cost of dealing with the various conditions of aging is set to escalate dramatically as the population ages. That's normally how these things are presented. One of the things I always get slightly tired of is this, there's almost a spin on this as though older people want to have 70% of all the items from the NHS and love nothing better than spending all their time in a hospital, whereas actually, like most of us, they simply want to never visit one, or if they do, go home as quickly as possible. The only people I've ever met who enjoyed being in hospitals were the people who worked there, but that's another story. And it's not just us. If you look globally, the problem is equally large. This is just the top 10 causes of death in high-income countries, data from a couple of years ago by the World Health Organization. And what these diseases have in common is, for all of them, age is a highly significant risk factor. If I was to draw you another graph there of the top 10 causes of death in low-income countries, about half of the diseases in the top 10 would still have age as a highly significant risk factor. And this is very much the elephant in the room around public health, because public health discussions tend to focus on what we think of as modifiable risk factors. Do you smoke? Do you take enough exercise? Do you consume alcohol moderately? And it is certainly true that your life expectancy, if you do all of these things, is much better than if you do none of them. In fact, it's about 14 years difference. And by way of comparison, the difference in life expectancy between the richest and poorest boroughs in the UK is about 9 years. So it is a big difference, and it is modifiable. But the idea that, you know, being overweight was the largest risk to your health is really wrong. And where you can see this playing out in perhaps a context that is present but sinks into the background has been through some recent disease problems. This is the age, mortality, and sex breakdown of COVID for the UK for the last 2 years. As you can see, essentially nobody under the age of 40 is dying of coronavirus infections, all right? And that's not unusual, because this is part of a general age-related increase in mortality related to infectious disease, where males show a greater susceptibility with age to infectious disease than females. And I'm happy to explain why that probably is in the Q&A if you're interested. But as you can see here from older data, 160-fold increase in mortality with influenza, 400-fold with GI tract infections. There's nothing odd about this virus. Nothing special at all. And what we call the mortality rate doubling time for COVID is pretty much identical to that for cardiovascular disease or anything else. In other words, particularly when you look at graphs like this, this is data from the Newcastle 85+ study, just looking at a cohort of people and counting the number of distinct chronic conditions they had at age 85. By the time you reach age 85, nobody is disease-free. The average person has between 4 and 6 chronic conditions. And one of the more amusing elements of this particular story was one of the leads who did this study actually had a cold and had to go to the GP. And when he turned up at his GP's surgery, there was a stern notice pinned up which said, "Appointments are limited to 10 minutes. Do not see the doctor with more than one condition at a time." And what he thought was, well, if that is the case, an average 85-year-old's GP appointment should be 60 minutes long. All right. Nobody has perfect health at the age of 85. Your risk of a whole variety of different conditions increases. That's why you look the way you do. And in other words, birthdays are incredibly bad for you. Okay. They are the non-modifiable elephant in the room of risk factors. And the reason this isn't put up normally is GPs don't turn around and say to you, "I've been looking at you and you've really got to cut down on your number of birthdays." Because stopping having birthdays altogether is really not an option. But what you can see, if you're actually ever interested in pulling this paper, it illustrates it very nicely. If you take 1,000 males of 35 and track them for 10 years, about 15 of them will die over the age of 35 to 45. However, if you take about 1,000 males who've never smoked and track them from the age of 75 to 85, about 450 of them will die. And so as long as there have been people we've known that something about your age is a critical determinant of how healthy you are. What then is this thing we call aging? And when a biologist is talking about aging, they have a very specific model typically in mind, because this covers aging in you and me and cats and dogs and plants and everything. Aging is just an increasing probability of death or sickness with increasing time in a population of animals or plants. And we call this the Gompertz relationship, after the early 19th century English mathematician who first recognized it. Gompertz curves or Gompertz relationships are terribly important to everybody, even though you probably don't realize it, because elaborate variations of Gompertz relationships are what people use to calculate your health insurance premiums, basically. This throws up an interesting couple of questions, which is, can you be non-aging? Whether you can or whether you can't, why does the aging process exist at all? How does it work? How does it relate to things we think of age-related diseases? What can we do to intervene in the root biological causes of aging? How would we do it? What might we expect to see in the broadest sense? And I'll try and unpack those questions over the next little bit of this. Because it wouldn't be a science talk without a formula. If you're interested, there is the formula that we use to determine if a population adheres to the Gompertz function. There will, of course, be a test at the end to see if you've remembered it correctly. So that, if you are interested, that is how you measure Gompertz functions. Because that's a logarithmic function, what we normally do is, although we refer to them colloquially as Gompertz curves, we don't draw them as curves. We log them, which some of you will be familiar with, and others of you will remember from maths O levels you were desperately trying to forget. Okay, and you end up with these Gompertz lines or slopes. And what I hope you can see, this is real data from these two lines, two things. The first thing is that these are not mortality curves for humans. You can see that from the fact that everything is dead by 1500 days. And the other thing I hope you can see is the slope of the line with the pink dots is different to the slope of the line with the black and blue dots. These are in fact two populations of brown Norway rats that once lived at the University of Liverpool, cared for by a colleague of mine. And because those slopes are different, in a very real sense, the aging of the cohort with the pink blobs was slowed. And it was slowed by an environmental manipulation known as calorie restriction, which we'll probably come on to a little bit later. If you don't like Gompertz curves, I like to put human faces on them. The angelic cherub on the left is no longer quite that angelic because he's taller than me and is my son. But when I took this picture, his chance of death was a fraction of 1% in the next decade. That is about the lowest chance of death you'll ever see. The slightly less angelic but greatly missed picture of the gentleman on the other side is my father, who died about 10 days ago. When I took that photograph, his chance of death in the next 10 years was 40%. And he kind of beat the odds, but not by much. And so that's what it means to be a member of a species that shows aging. So are there any species that don't? And if you look across the biosphere, aging is extremely common, but it isn't universal. So if you want a couple of examples of well-known aging animals, some of you who did science at school may have come across an organism called Hydra. It's a little blob of jelly with some stingers that sometimes lives in school science projects. These animals showed no mortality over an extended period of follow-up, but the champion is probably an organism called Arctica islandica. If you watch Family Guy, it's the quahog, and if you've had clam chowder, you have eaten these organisms. And the organisms in your bowl of clam chowder were probably older than you are. The very oldest Arctica are so old that Shakespeare could have had them in a bowl of stew. And What makes both these organisms interesting is that they show a fixed chance of death per year, rather than an exponentially increasing one that we see through most of our lives. So these organisms show what we sometimes term a Gompertz flatline. And because their chance of death is fixed and very low, that's why you can have Arctica living for 400 years. And as I hope the bowl of clam chowder demonstrates, just because you're non-aging, that doesn't mean you're immortal. And extending lifespan is not equivalent to immortality, which is a point I will return to at the end about how we should think about what we're doing. And so why does this Gompertz relationship exist? And why are there exceptions? And there are two basic evolutionary biology explanations for aging, both postulated around about the same time, and both have stood up pretty well. One, very famously proposed by the British biologist Peter Medawar, goes a little bit like this. It's called the mutation accumulation theory. It's that natural selection is dreadful at removing any genetic variation that only acts after an organism has reproduced. All right. Natural selection only measures fitness, which is understood as survival plus reproduction. So if a gene doesn't exert an effect until after an organism has reproduced, regardless of whether that organism shows aging or not, natural selection will not be able to remove that variation. And Medawar took this idea and generalized it and said, well, okay, maybe what we think of as aging is just the accumulation of these crummy, late-acting, bad genetic variations that natural selection can't get rid of. And a few years later, a very famous evolutionary biologist called George Williams took this idea and kind of supercharged it and said, okay, mutation accumulation considers a genetic variation that does nothing during the reproductive part of the lifespan. It just coasts along. Imagine a genetic variation that makes you a better replicator early on in the life course. This will not coast. This will be very heavily selected for, even if it is associated with bad stuff happening later on, because for most organisms in the wild, there is no later on. They are predated, they fall off cliffs, etc. And there is good experimental evidence in the species we've looked in for the operation of both of these mechanisms, though the proportions in which they seem to contribute to the aging of a given species vary. And they almost certainly vary as a result of that species' evolutionary history. This also contains the prediction, although I won't get into it unless we ask in the Q&A, that non-aging organisms will usually get outcompeted by aging ones, but there is an escape clause that allows non-aging organisms to exist. As a kind of health warning, anybody who's met humans knows that humans are weird. But what most people don't know is that human evolution is really radically weird by comparison to most of the species that we study in laboratories. Specifically, humans went through a massive genetic bottleneck about 70,000 years ago. Everybody alive today descends from under 1,000 individuals. And this is very unusual. And this, together with this is some work that we've done on another shift that makes humans weird, which is known as population type shift. We do have some work on the evolution of human aging that should be coming out soon. What this means is that humans have a very odd evolutionary life history, and this may mean that the mechanisms that regulate aging may differ in importance between humans and other species. That is an open question. We don't know the answer. You can go forward in a spirit of hope and say we're all the same. You can go forward in a spirit of pessimism and say humans are different. Doesn't matter. We will bottom it out, but it's worthwhile knowing. So what does Gompertz measure? Gompertz just measures death. And this leads to an interesting intellectual question, which is, if Gompertz only measures death, what does that mean for aging? Is there such a thing as an aging process? Is there just disease? Is there something in between? Why does this matter? And it matters because if there's only age-related diseases, then you're wasting your time working on the aging process because it's not there. On the other hand, you could say, if there's an aging process, perhaps working on age-related disease was the thing you did wrong, or is the distinction itself a false dichotomy, which frankly is what I think. And this throws in some interesting things because, as Karl Popper would have told you, experiments don't lead to theories, theories lead to experiments. So how you conceptualize aging also dictates how you study it and also dictates what you think you should do about it. Humans have been arguing or wondering about aging for as long as there are recorded writings about later life. A good entry point is Galen. He produced an argument that has had traction for realistically about 2,000 years. And medical students produce this spontaneously and somewhat irritatingly. Galen's entry point goes a little bit like this. I can't tell you what aging is, but I can tell you what disease is. Disease is disordered or abnormal function, but aging is universal. That which is universal cannot be abnormal by definition. Therefore, aging is a disease, is not a disease. Okay? And you know, all that's happened in the intervening 2,000 years is that Nathan Schoch, a very famous gerontologist, has said exactly the same thing, but with a lot more words. All right. And this is not a trivial point. The interesting thing about this is just reasoning. It does not touch the biology at any point. All right. And this is kind of how people, if they haven't thought about it, tend to think about aging. That there's this kind of natural process that happens to everyone, and there's diseases that happen to some people but not to others. This is wrong. All right, it's flat wrong. There is another variant, I would argue, of flat wrong, which is even more interesting. And this was probably put forward in its purest form by this gentleman, Richard Doll, who published a somewhat infamous article, "There is no such thing as agging," in the British Medical Journal. Now, as far as I'm concerned, when the E has fallen out of aging in the British Medical Journal, the abomination of desolation is in the holy places. But what Doll in fact said was the fact that lots of adult diseases tend to arise in the same part of the lifespan isn't good evidence that they have a common cause. I'm particularly fond of this article because it's accompanied by this fulsome picture of Sir Richard, clearly not undergoing aging at the age of 85. All right. So what is his argument? Doll is not a fool by any stretch of the imagination. He's one of the great epidemiologists. He's the chap who showed the link between smoking and lung cancer. His mental model is something like this. You start off healthy and young and you end up sick and old. You start off without cardiovascular disease, there's a process, you get it. You start off without cancer, there's a different process, you get that. So on and so forth down all the list of diseases. There's no space for anything else. This, by the way, would be a pretty good conceptual model of infectious disease. You start off without athlete's foot, and there's an infectious agent, and you get that. You start off without measles, and there's a different infectious agent, and you get that. This would have been perfectly reasonable to stick up in 1967. But what made this article a bit of Bang's head on, keyboard, is that by 1997, when I read it, it was untenable and it had been untenable for 10 years. The model is a good model in a Popperian sense because it makes a strong prediction. If every disease has a distinct cause, then a single change shouldn't fix or cause more than one of them. And what made this untenable was that you could not square it with the data that was coming out of biology. On the one hand, you were able to isolate single gene mutations, first of all in worms, then in flies, and then in mammals, that made animals live much longer. And the reason they lived much longer was they had been made much healthier. They showed reduced incidence or severity of multiple pathologies with a single genetic change. You cured or fixed multiple things. It was also not compatible with this. This is a human genetic disease called Werner's syndrome. For the avoidance of doubt, the gentleman with Werner's syndrome is the gentleman on the right of the picture. The gentleman on the left just has a weight problem and a really bad 1980s tie that I don't wear anymore. But what makes that picture interesting, apart from the fact it's receding in time the more often I show it, is that the two of us are about the same age when that photo was taken. We were both about 30. And Werner's is a single gene mutation that is associated with the premature aging of multiple tissues, but not all of them. So on the one hand, we have single gene mutations that make you healthy and delay aging and make you live much longer. And on the other hand, we have single gene mutations that accelerate aging and cause multiple pathologies. This is not compatible with this kind of parallel track model. And if you look in broader populations, you can see the same thing. The long and short of this paper is, if you correct for everything else, if you get cancer, your chance of Alzheimer's disease is significantly reduced. And that's once you've corrected for the obvious things, like if you get stage 3 breast cancer in your 20s, you won't live that long. And if you get Alzheimer's disease, your chance of getting cancer is significantly highly reduced. And people think of Alzheimer's disease and cancer as separate conditions. There's no reason that your chance of getting one should reduce your chance of getting the other. And so, just to summarize, aging doesn't look like this. Looks more like this, where we have a few things, you can think of them as aging mechanisms, or as I do, as health maintenance mechanisms, that act to keep you healthy. Problems arise as these start to fail. And when they start to fail, we see a lot of things going wrong with mammals and with us. Some of them are things we've chosen to call diseases. Some of them are things that we think of as natural changes, grey hair and wrinkles, just because everybody shows them. And the others are the ones that we find so damn hard to classify, like hearing loss or immunosenescence, which is responsible for the infectious disease slides I showed you at the start, or even things like menopause. All right, but acting together, these failures of health maintenance lead to sickness and to mortality. They are driving the Gompertz curve. So what are the mechanisms that maintain health? We have not discovered all of them. This is abundantly clear, but I feel obliged to say it. We do, however, have a good handle on at least some of them that have big effects. There's a number that are summarized in that slide. That image is shown a lot because no scientist can draw as well as the artist who did that for Cell. Okay, but it is now, 10 years out of date. I'm going to discuss just two of these potential mechanisms. One concerns how cells sense nutrients. The other concerns how cells and bodies act to prevent cancers. And so, again, we've had the mathematical formula. It wouldn't be a science talk if it didn't have a large, incomprehensible genetic pathway. You'll have to trust me on this one. This is the pathway by which your cells sense nutrients. All right, and it converges on the big red circle with the words TOR in it. And the reason I've put it up is when you identify a mutant in the lab, whatever you want it to do, it's a little bit like owning a piece of alien technology. You know what the mutation does, but you don't know what the mutation is. And so an awful lot of the nuts and bolts of science, when you isolate interesting mutants, is trying to work out what the damn thing is actually mutant in and what the mutation does. And all of the long-lived mutants, or most of the long-lived mutants we've found so far in lower organisms, map into this nutrient sensing pathway. which is why I've put it up there. All right, and this, whoops, that was not something I expected to happen. Thank you. And you will recall that in the diagram, there is a big red blob with the word TOR on it. TOR is a protein, and it stands for target of rapamycin. TOR is the central node in protein synthesis. And rapamycin is a compound made by fungi from Easter Island that is now a drug. And if you take rapamycin and you treat animals at low doses with it, particularly mice, you mimic the effect of being a long-lived mutant. It leads to a 15 to 20% increase in mouse lifespan. And the reason those mice live much longer is because they are much healthier. All right. And back in 2009, this was reckoned to be one of the most significant scientific breakthroughs that have been made that year. If you're interested, that's just some of the survival data. And what is interesting, as I said, is that rapamycin improves health. In animal models, it seems to give favorable outcomes in models of Huntington's disease, and it appears to have a highly favorable profile for cognitive deficits in treatments of cognitive impairment. One of the really useful features of rapamycin is that if you give a low dose of rapamycin to older people for a brief period of time, about 6 to 8 weeks, it's very well tolerated, and you then, this was a few years ago now, vaccinate against the flu, what you find is that people who could not make protective antibody titers then made them, and they were protected against multiple strains of flu. Okay, and flu was the great unacknowledged killer of older people. Back in 2018, there were 50,000 excess deaths from the flu in older people, and we did not put the entire country into lockdown over it. We just sent people home and told them there was nothing we could do. And there is some real hope that targeting this pathway won't just enhance your immunity, it will enhance other features as well and get rid of some of that chronic disease burden. Thus far, nutrient sensing. All right. Tumour suppression works a little bit like this. In the normal course of your life, you lose cells. That loss is balanced by cell division. You pick up most of your mutations in your DNA when cells are dividing. All right. And then you're in a bit of a bind, because you have to have cell division to replace lost cells if you're a long-lived organism. But each time you divide, there's a chance you'll pick up mutations, and cancer is a mutational process. How then can you get around this? By building in mechanisms that count the number of cell divisions or allow you to stop dividing if something looks like it's gone wrong. So in the normal course of life, you lose cells. That loss is balanced by cell division. Cell division is actively counted. After a fixed but variable number of divisions, irretrievable exit from the cell cycle is signaled. I will never escape from ringtones. Normally it's students, but never mind. Okay, and even when everyone's on mute, there's a ringtone. Okay, so cell division monitored, exit from the cell cycle signaled, forming things we call senescent cells. Senescent cells do bad things, and they do bad things because they wish to signal to be cleared by the immune system. But your immune system is itself made of cells, and it is aging as well. And so the result is you go from having essentially no senescent cells when you're young to suddenly starting to fill up with them in midlife, as a combination of both making more and clearing less. You can see these cells, they're the blue blobs in these little images, and the holy grail of senescence research for many years has been either to fill an animal up with senescent cells and see what happens, and you would get something like Werner's syndrome, because Werner's syndrome is probably caused by the accumulation of senescent cells, or to take them away and see what happens. The latter study was done a couple of years ago, and this involved making transgenic mice, a very clever couple of researchers, Androyson and Kirkland. The two mice in the picture are litter mates. They're the same age. The mouse on the bottom is the control. The mouse on the top has had its senescent cells removed by adding a triggering drug to the drinking water. I think you can see which one would be preferable as a pet. There are oodles of data with this transgenic mouse model because you can do two different kinds of experiments with it. You can remove senescent cells all the way through the animal's life and see what happens. You can let the animal fill up with senescent cells, then delete them, and then see what happens. In both cases, you see a dramatic improvement in function. The data I like most are wheel running. If you delete senescent cells from these mice, the old mice run about twice as far and twice as fast as their undeleted litter mates. And this is voluntary wheel running. No one is making these animals run. They're running more because they like it and they feel better. And if you scale that up to older people, it is the difference between being able to live independently in your own home and having to sell up your life's possessions, downsize, look at sheltered accommodation, and eventually look at a care home where your survival time on average is 24 months. Okay. I am glad to say that rapid progress is being made in translating the findings we had in the mice into humans. The first, what we call open label trials to remove senescent cells were done 18 months ago. I believe there are either 30 or 60 trials of this class of drug, which we now call senolytics, happening now. Most of them will fail. Most clinical trials fail. We only have about 1,200 drugs, and that includes aspirin and morphine. But one or more of those trials will succeed. And so this is roughly, to use an analogy I often go back on, we are standing roughly where people in the late 1940s stood with antibiotics. This is penicillin for old age. Rather like penicillin didn't fix every problem with bacterial infections, senolytics won't fix everything. But rather like if you were a time traveler with a bacterial infection and you could pick any year in which to land to get it treated, you would sure as hell pick some point post 1950 rather than pre-1950 to do that. That is where we are. And I'll talk a little bit about some work from my own lab and my own collaborators in this. We think we identified a novel one of these health regulatory mechanisms, which is dysregulation of something we call RNA processing. Just so you know, what happens is there is something called the central dogma in biology, which is DNA makes RNA makes protein. You are much more flexible in exploiting this central dogma than, say, a bacterium. It just makes DNA, which is turned into an information transfer molecule called RNA, which is turned into protein, which does the work. For us, it would be DNA makes an RNA, which is made into a lot of different, subtly different RNAs that allows you to make lots and lots and lots of cool but subtly different proteins off the same bit of information. And that process is RNA splicing. And RNA splicing is one of the most heavily dysregulated processes in mammalian aging. It's all handled by things we call splicing factors, and splicing factors are heavily altered in senescent cells. And so my colleagues at the University of Exeter, all of the splicing factor work is the result of a brilliant biochemist, Professor Lorna Harries, who's devoted her life to understanding this. But she came to see me because we had developed some novel compounds, and Lorna had seen some straws in the wind that said these affected splicing. And so she took our novel compounds, poured them on senescent cells with our assistance. They did alter splicing factors, and what that did was it reversed senescence. So rather than a senolytic, which is a bit like an antibiotic for senescent cells, it kills them, our compounds stop them being senescent, stop them doing bad stuff, and put them back to work. And there are clinical indications very clearly where you would want to do that. And if anybody is interested, I'll tell you about it. So the future's very, very bright for doing things about the chronic disease and morbidity burden of later life. What will happen? Okay. These are 4 scenarios for what the future holds. One at the top is the situation now. Average life expectancy is about 85, and you spend about the last 10 to 15 years of that in ill health. I actually am planning my retirement around that graph. Okay. One scenario that is plausible, that is, we see it in experimental animals, is that we hold life expectancy the same, but crush the period of ill health to maybe 12 months. And we call this compression of morbidity. The other scenario, which is plausible, is also seen in experimental animals, where we keep that, 15 years of ill health, but we add 20 years of healthy lifespan. That is compression of morbidity in another way, so we call it extended lifespan instead. What you don't see in any experimental system is the thing people worry about, which is you add 30 years to lifespan, all of which is a period of ill health. So you extend 30 years with arthritis. Never happens. Okay. The nightmare scenario is just that. It is a nightmare. It is not connected to reality. For the first time a few years ago, colleagues in the States tried to take a look at what this would mean. If we could translate modest findings in improving healthy lifespan that we see in the lab into human populations. And what happens, perhaps unsurprisingly, is improving health span has the largest impact on the number of healthy old people. It also saves enormous amounts of money. Even if you pay older people the entitlements to which they are due, the US saves $7 trillion gross, $4 billion gross, $4 billion net out to 2050. It's bigger than any other delay scenario. And so what does that mean? It can save that $4 trillion. $4 trillion translates to being about that, about 40% of all the gold, never mind, about 30 years of clean drinking water, about 1.7% of total global wealth. And those figures are now considered to be a conservative estimate for what the savings might be. One argument using a different economic model is every year we can add to healthy life expectancy saves the US $1 trillion. And that is money we will have to spend on the global aging population otherwise, because by the middle of this century, over 65s will outnumber under 16s throughout this planet for the first time in human history. And I think that's a huge triumph, but we are stuck with the problem, all right? Which is why I always say a better world for older people is a better world for everybody. We crack this, we free up enormous resources we can put on other problems. We don't crack this, we've got to spend this money to go the distance. And so this brings me really into the last 10 minutes, 5 minutes of the talk, where I thought, given an interested audience, it's always worthwhile discussing these things. Aging research is now in a translational phase. We are starting to do things, and I think we should start to think about them, basically. What are the ethics of the work? Now, key point to bear in mind, because this is the point at which rational discourse is rapidly overtaken by the internet. All right. Key point, the ethics of true immortality differ from the ethics of limited lifespans. It doesn't matter if you live a week or 100,000 years. There are no unique ethical problems, and nobody is going to be immortal. So let's just deal with that. You do get a group of people who are very explicit and very vocal about their desire for indefinite or 1,000 year lifespans. They dominate media coverage, they dominate the internet, and there's a lot of loose comment about what we're doing without looking at public opinion. Why am I engaging in this at all? Because scientific research is predicated on a social contract, that the studies we support as a society or the studies we permit as a society serve our broader social interest for a varying range of definition. So what do we think? Well, most people think science is important to improve the quality of life of our old people. I certainly do, or I wouldn't have gone into science specifically to do that. There's a lot of support for it. There's a lot of support for public benefit as the yardstick, and taxpayers should be paying for it. Interestingly, the idea that taxpayers should be paying for aging research doesn't appear to have reached the Treasury yet. This slide is not an eye test, by the way. Okay. When I drew this up, the big blue blob was the UK budget. Then next below that was the NHS budget, which was the largest on budget item. Then there was the amount of the NHS budget we spend on old people. Then there was the science budget. And that thing that looks like a dot of dust on your screen was the largest interpretation of the aging research budget we had. And there was when I was doing this, there was a gentleman called Vince Cable. You may remember him. He was a member of a popular comedy troupe back then. But he made a speech in which he said there was a strong case for identifying broad problems like the aging population. So that's what you get for being a broad problem. I'm incredibly glad he didn't consider us to be a narrow issue. Okay. And so what do people want? A majority of people don't want medical treatments that set a minimum lifespan at 120. About 70% of people want to live somewhere between 80 and 100 years. With sustained youth, about 80% of people want a lifespan of 120 or longer. However, only a minority of respondents want the kind of unlimited lifespans that you see on the internet. Okay, and so, and perhaps unsurprisingly, what most of us want is a healthy old age. All right, but some people clearly don't. They really want the 10,000 year lifespans. And so this poses an interesting question that should also interest this audience. It certainly interested me for many years, which is the people who want unlimited lifespans think the people who want limited ones are dumb. And the people who want limited lifespans think the people who want unlimited lifespans are selfish. So what's going on here? Why do people think the way they do? All right. So to be a humanist is to make an ethical decision based on reason. So what are other people's reasons? And I'm going to give you 4 reasons to finish off with in declining order of what I think are probable. All right. And this is all of the bits of probability, and it taps into an area that I'm interested in anyway in another life. The first one is this thing, the pro-aging trance, most associated with this gentleman, Aubrey de Grey, also the most vocal proponent of the idea that the first person to live to 1,000 has already been born. Okay, and basically Aubrey proposes that What he calls the pro-aging trance is a rationally adopted response to the historical immutability of aging, or as he put it many years ago, the desperation that almost all people have to put aging out of their minds, pretend it's some kind of blessing in disguise, so that they can get on with their miserably short lives without being preoccupied by the terrible thing that awaits them. People with a broad frame of mind may immediately recognize the familiarities of this idea to the classic Marxist one of false consciousness. If only the workers would wake up, they would realize how they were being oppressed. I don't think Aubrey has read Marx, but he's mirrored the, they don't think the way I do because they have been lulled into this. The only problem is it's inconsistent with the data. Okay. It's normally used to explain why we don't get any money, but 90% of the public think we should. And not being of a kind of exuberant frame of mind, I would simply suggest that bad marketing is not false consciousness. And you cannot rationally choose to put aging out of your mind because it's incompatible with the highly intrusive nature of distressing thoughts. I should love right now to put my father's death out of my mind. I simply can't do it. A better explanation is that growing old is simply not something people obsess about. It's, you know, it's what we call a low salience issue. However, people do kind of obsess about their health, or at least about 30 times what people do. So this is a framing issue for the field. So Aubrey may be morbidly preoccupied with death, but most of us aren't. It's not this other thing, terror management theory, which you may have heard of from the 70s, the denial of death by Ernest Becker. Individuals are so distressed by their own mortality that they minimize existential threats and strive to get a big statue built after them. Okay. This is taken apart on evolutionary psychology grounds so severely that there are just twitching, bloodied fragments left on the roadside. So I won't go into that, though I'm happy to, if you will. It's probably not something we call the naturalistic fallacy either. The naturalistic fallacy is the conflation of things we consider natural with things we consider to be good. And if you remember, aging is conceptualized as a natural process. To illustrate the naturalistic fallacy, I've put up two pictures. At the top is the Japanese tsunami of a few years ago. Tsunamis are 100% natural and therefore good. And at the bottom is my library, 100% unnatural and therefore bad. We must promote tsunamis and get rid of libraries. That would be the naturalistic fallacy. Naturalistic fallacy kind of helps here, because if you look in polling data for people, about 58% of respondents think that lifespan extension treatments are fundamentally unnatural. About 3/4 of people who think they're bad think they're unnatural, but so do 43% of people who are itching to take them. So it's not it's in there, but it's not a major puller. And the most likely, to my mind, and I say likely, framing that explains the difference between the people who can't wait for 10,000-year lifespans and the people who are totally unmoved by them are what are called Maslow-Schwartz values. And some of you may have heard of these and some of you may not. The Schwartz-Maslow theory derives from Maslow's hierarchy of needs. It breaks human values down into a set of culture-independent ones, openness to change, self-enhancement. Individuals do show dominant Schwartz values. It boils down to everybody has the same basic set of human needs, but in each individual, certain needs will be dominant. If a proposition accords with an individual's dominant values, it's salient and you're on message. If it doesn't match, it's ignored or rejected. Maslow-Schwartz is currently, to my mind, one of the best predictors of decisions, particularly contested ones. Brexit, for example, is a classic Schwartz value conflict. the highest predictor of how you voted are your Schwartz values. All right. And it also correlates about Schwartz values correlate about 80% with your socioeconomic status. All right. And the fact that people don't recognize that working class and middle class people, by and large, have radically different Schwartz values is what is driving this dynamic, famously summed up by Crouchstev, which is a world in which the populace are becoming anti-elite and the elite are becoming secretly anti-democratic. I thought I would try and illustrate this because it is important with reference to three scientists, if you're interested in thinking about why people think the way they do. Occasionally these are actual Schwartz-Maslow data for three scientists. One of them is me, actually. All right, but the reason I thought I would put this in is to try and disarm a couple of things. Each of these people is a scientist. They work in different fields, okay? All of them, by their IQ scores, are highly intelligent. So they're not stupid and they have very high levels of expertise, all of which are relevant to the question. Now, normally with scientists, I would say, what are they like at a conference? But in order to understand what they're like at a conference, you'd have to have gone to a scientific conference. So I thought I would illustrate the Maslow-Schwartz differences with the film Avatar, if you've ever seen that. Basic summary of Avatar is humans who desperately need a resource turn up to this planet called Pandora that has intelligent but technologically primitive life forms on it, and the environment's horribly hostile. All right, and the humans are after a mineral below the surface called unobtainium. So how do our three scientists on the spaceship respond to the Pandora paradox? Let's take number one at the top first. Number one, because of those power and achievement scores, is either in command of this mission or sure as hell wishes they were. All right, not terribly interested in visiting the planet's surface, low stimulation, doesn't really care that much about the Pandorans, okay? Not very universalist, not very benevolent, very keen on securing this rare mineral, and thinks outside the box because they have a very low tradition score. This will be the person who starts to commission the feasibility study of dropping the asteroid on the Pandorans so we can wipe out the irritating ecosystem and then mine the stuff we want and go home. Okay. The next one down, number two, is an equal bet for being in charge. Number two also has power and achievement scores. Number two is even less keen on getting off the spaceship than number one, okay? Those stimulation scores of 0 and sub-0 are quite impressive, all right? These two are never getting off the ship. However, number two is also quite traditionally minded, has a kind of, still wants security, but knows that wiping out entire ecosystems is just wrong, all right? But is sufficiently close to number one to know arguments that will work on number one, and is likely to say, don't drop an asteroid on them. This ecosystem could be incredibly valuable to us. Let's send down lots of survey teams and start bringing back samples of the flora and fauna. And no, I'm not getting on one. And this contrasts very sharply with number three. Number three is a low-level technician sitting somewhere in the bilges on this spaceship, not because they're stupid, but because they're not interested in getting on. The reason number three is here is number three is a total adrenaline junkie. Okay, they signed up to be on the spaceship so that they could be on the first shuttle down there. They're not interested in gathering fauna and flora particularly. They're interested in wild camping and hopefully going for a party with the aliens. All right. And the reason I've taken that slightly odd scenario is to illustrate what happens where if you have no differences in cognition and no differences in expertise, you still get radically different outputs to a scenario based on your Maslow values. Nobody has measured the Schwartz values of people who want lifespan extension versus people who don't yet, but they have measured attitudes to the death penalty, and that is predictive of Schwartz clusters. So people who are for capital punishment are much less likely to want lifespan extension than those who are against it. And this throws up an interesting question or comment, which I thought I would leave you with. There is no right or wrong set of Schwartz values, because they are not a hierarchy, they are a continuum. Okay, anybody who adopts a course of action that accords with their dominant Schwartz values is a rational actor acting in their own self-interests. So neither the lifespan extension people or the limited lifespan people are unethical, nor are they necessarily low information voters. Okay, to use another term that's used about Schwartz-Maslow groups that people don't like. All right, you could almost say, going back to the humanist thing, that the limited lifespan people are humanists and the lifespan extension people are transhumanists, which would be the closest thing. And so that's a little bit about why people think the way they do. I introduce it because it merges my interest in the genetics of how humans take decisions with taking decisions about things that will affect us all. That's basically the summary of what's going on. The immediate research challenges, whether you want a 10,000-year lifespan or simply a healthy old age, are identical. They will diverge over human history, I think, but I, for one, have absolutely no intention of being around by the time they do. So there you go. That's all, as they say, from me. I can now stop sharing. If anybody has any questions, thank you for listening, and I'll try and address them.
Thanks very much, Richard. Fascinating and interesting, and well worth looking at this video that's recorded to go through it again, because there's a lot of information in there, but I managed to get quite a bit of it, and very fascinating. So any questions? Yes, Richard's in charge.
No, just please unmute and ask away if there's anything you want to know, Mark.
Yeah, I'd absolutely love to have the longer life, healthier lifespan. Absolutely. One of the things, the factors I don't think you touched on that I think is a fear, is that the technology is so expensive that all of the worst and most unpleasant people in society, the ones that we kind of need, the leaders you always hope would at least die off in a horrible regime, will be the very ones that will be able to afford it, whereas the normal people might not.
Let me cut you short. Okay, the technology to achieve this right now is dirt cheap. Costs about £10 a day.
And a £10 a day.
Allow me to explain why. Allow me to explain where that comes from. Okay, Rapamycin. Okay, I'm not, by the way, the purpose is saying everybody run out and buy Rapamycin. But okay, let's see. I showed you some data with mTOR inhibitors, Rapamycin to boost immunity or this sort of thing. Okay, Rapamycin's an off-patent drug. You can get it in every you can get it in NHS hospitals for about £10 per patient per day. All right. In contrast, it costs about £60 per day to maintain somebody with mild cognitive impairment. All right. I think what your question is very interesting, because it throws up something that comes up a lot, which is this is a highly desired thing, so it must be expensive. And my answer is this: it may well be highly desired, but it's not expensive because we've been too dumb to find the answers for the last 2,000 years. And I cannot actually illustrate quite how little interest in aging research there has been in the broader scientific community. My lifespan, when I started out, I was taken to one side and told that choosing to work on the biology of aging was a waste of a good mind in a pointless backwater. And there is an equally famous, I love this story. I didn't mean to have a mare, but it is kind of, you're the speaker, 20 humanists have to listen to you, it's the law. But if you're interested in this, I actually found an even worse version of the kindly old professor saying, look, don't ruin your career. If you want to end up Sir Richard Faragher, then aging research is not for you. And it's a Society of Experimental Biology Proceedings series from 1967. And it's a very famous conference. It's organized by a very famous gerontologist called Alex Comfort. And if you're interested, yes, it is the one with the joy of sex. He had a parallel publication history. And he organized a conference to try and drum up interest in the broader scientific community on studying problems of aging. And one person who was there, as Comfort wrote it up, turned around to him and said, a competent biochemical team could have all this sorted out in a fortnight. And the interesting thing for me when I read that was that Comfort didn't make the obvious rebuke, which to me is, I presume you run a competent biochemical team. Now, I do appreciate you've obviously got much more interesting scientific things to do. But given that somebody who cracked the problem of human aging wouldn't bid fair just to be considered the most brilliant scientist who'd ever lived, they would probably be pushing at the top 10 for the most influential humans who've ever lived. And that, to my mind, is up against some pretty stiff competition. Why don't you take 14 days out of your busy schedule and put your really competent biochemical team on it? And even if it takes you 3 weeks, who cares? But that conjures up, the reason we are so far behind is nobody was interested. Okay, and so, yeah, the early innovations will be cheap. Okay, because knowledge is cheap. Penicillin is cheap. How much would you have paid for penicillin in 1900 if you had an infected limb?
Can I just ask then, is it, I mean, literally, can I go out and buy Rapamycin now?
No, you can't, because it's a prescription-only drug, and you certainly shouldn't. Okay, but the short answer is, are there cheap drugs that could do this? Yes. And I always turn around and say this, because there is this real kind of thing about why would you want to, and there is a thin line, people just don't think about stuff to do with aging the way you would think about other medicines. And all this is the next generation of medicines. Okay, imagine, turn this conversation to something normal. I'm hypertensive, so I take an antihypertensive. There was no point in me taking it beforehand. And somebody who is prophylactically taking antitensives and SSRIs and things like that isn't health conscious, they're a hypochondriac.
But aren't you saying that we're all developing large accumulations of senescent cells?
Yeah, and what I'm saying is this, okay? We wait for the clinical trials, the licensing, and the prescription against indications, because that is what healthcare professionals do. All right? And that's it, just stunned silence.
Well, no, but so you're saying that the timescale on that is before I completely fill up with these.
Yeah, okay. I mean, if you're interested, there is something critical happening now. I mean, if you're really interested, there's something critical happening now. All right. Here's a fun question for you. If you had a drug that added 50 years to lifespan, how would you know? You can't give a drug to people for 50 years. All right. And I love this. This is a piece of sheer genius. It's one of those things where I simultaneously love it and I'm still simultaneously jealous as hell that I didn't think of it, because I deserve to. Okay. And the average duration of a clinical trial is about 24 months, yeah? 2 to 3 years typically for a clinical trial. And clinical trials are really expensive. So how can we crack this? And the person who is most directly responsible for doing the conceptual work around this is a very clever man called Nir Barzilai, who's over in New York. And he reasoned like this: the time at which you develop your first age-related pathology or impairment is very variable from one person to another. But the time from first impairment to second impairment is tight. It's about 24 months. And so a drug that lengthens healthy lifespan will lengthen the time between first impairment and second impairment, from any first impairment to any second impairment. And this is the idea of something that's known as the targeting aging with metformin, or TAME study. Okay, and TAME is radically different from any design of clinical trial that's gone before. So what you would normally do, if you've got a drug where you think it may improve migraines, you'll take, 4,000 people who have migraines. You'll give 2,000 of them the drug and 2,000 of them sugar pills. And you won't know who's got the drug and they won't know who's got the sugar pills. And you'll monitor the frequency of migraines, and then you'll and if there's benefit, you'll deblind the trial. This is any first event. They're looking at recruiting several thousand older people who all have a single impairment. Half of them will get sugar pills, and half of them will get a drug called metformin, okay? Because metformin is known to affect some of these, and it's another one of these cheap drugs. And they will then be followed. Trial protocol is designed. The only thing that we're looking at is funding. If you've got 30 million lying around in pocket change after this, and you'd care to help fund TAME, please donate to the American Federation of Aging Research. I'm on the board of directors. It's the leading charitable funder for aging in the US, and it is actively fundraising for this at the moment. Now, sooner or later, and hopefully sooner given where we are, TAME will get off the ground. And that means that we will be able to start to unpick which conditions work best, which indications. And I am positive that what will happen is we'll see some successful outcomes. I'd be very upset if we didn't. Okay. I would imagine that if there were positive outcomes, it would open the door to a whole slew of other trials. And what you would then do, and what would then happen, would be metformin would be the comparator. So when I said there are 60 ongoing senolytic trials, this stuff is happening fast. That, that normally takes about 10 years to develop things, but the first but that's, we could be faster than that. This is going to happen within our lifespans, without any doubt. The questions that you then get into, which become important, are this. You then start into the whole messy business of which patient subset benefits from which drug. Now, to give you an example with me, because I'm the best person I know, I mapped my own genome, which is how I found out I had hypertension, because my GP had forgotten to take my blood pressure and just kept saying I was stressed. And I also was able to use that to map back to which drug I should take. If I'd been given another common one, I probably wouldn't be here, because I carry a genetic variant that renders me very prone to fainting on an otherwise normal drug. And so what would have happened would have been, I would have been driving home from the university one day at 70 miles an hour on the A27. I would have blacked out at the seat, in the car seat, and I would have been written up as a road traffic accident. But what would have killed me was the wrong drug, which is why you don't go around buying Rapamycin off the internet. But it also illustrates why we do things like that. And an awful lot of the stuff that guys don't see is digging into which patient subset will benefit. And we are just starting to do that now. But one of the things that will happen is some patient subsets will benefit, but ultimately the door's open now. I think that's worthwhile bearing in mind. The door is open now. Okay. Hello, David.
Hi.
Hello, Anne.
Thank you very much indeed. Very enjoyable. Some of it went quite fast. I couldn't understand why the saving from making people or allowing people to get older was occurred, why it wasn't just transferred to a later date.
Okay. Why it wasn't because in fact what happens is you don't die because you're old. You die. The thing that costs being old doesn't cost any money, put bluntly. Being sick costs you money, and we're so used that includes pension costs. And there is another thing that's worthwhile doing with pensions, which is you can separate pension. This is okay. Well, remember I said even dealing with the entitlements due to older people. Okay. Let's put it this way. Pension costs are a fraction of healthcare costs. NHS to just, you know, about half the NHS budget is
okay,
spent
but
on
on the point of you've transferred everything to 10 years later or whatever it is, 20 years later. So why is that cost not the...
That isn't what I've okay, let's put it okay. Do you understand what I mean when I say compression of morbidity?
Yes.
Right, okay. Let's look at it this way. Compression of morbidity. You're 85 years old. Right now, you spend about 15 years in ill health, yeah?
Yes, I understand that, yeah.
Your ill health costs a lot of money. Your healthcare costs go up markedly in the period that you spend ill, all right? So imagine that you spend a week ill. The saving is monumental.
But in your picture, I thought the desirable outcome, you had the same width of red illness, but but you had an extra chunk of...
No, it was much compressed. It was much compressed.
Oh, it looks like
as
that.
well, was it? Oh,
yeah,
okay.
that is compressed. There are two separate.
If it's compressed, I understand.
There are two different things, and they achieve the same. One is compression of morbidity. Okay, instead of having 15 years of ill health, yeah, you compress that to 15 minutes. All right, that's not going to happen. That's you know, that is an exaggeration to try and get the point across. Yeah. Okay. The other variant of compression of morbidity, which people find harder, is the one we call extended lifespan. I'll keep your 15 years of ill health, but I'll add 1,500 years of healthy lifespan. Okay. You see, I've done the same thing. I've just lengthened the healthy period. Well, you can either compress the sick period or lengthen the healthy period. It has exactly the same effect. And what you see in animals is a combination of those, or one or the other. But either way, you have reduced either the absolute or relative period of ill health. And it's the ill health that costs the money. One of the things to bear in mind with pensions, by the way, because this always gets me, is your pension is completely uncoupled from your physiological status. All right. I don't know. I guess most people remember that pensions were brought in 1911, Lloyd George. Yeah. No. Okay. People's budget. The first old age pensions are brought in with effectively with Lloyd George in 1911. All right. And that's where you get the, if I remember correctly, that's where you get 60 for women and 65 for men. All right. But at the point that those pensions were brought in, life expectancy was 52. Okay. So let's put it this way. It's a nice thing to know that, you know, if it's 1911, it's a nice thing to know that if I reach the age of 65, I'll have an old age pension. But I've got way worse than a 50% chance of getting there. Now we retire at 65 and life expectancy is 83. Now, if we were to adopt the kind of Edwardian vision of a pension, Imagine there were no pension, there were no state pensions, yeah, at all. Everything's private provision or whatever, and you can retire. I mean, I plan on retiring at 61. Okay, but that's because I've managed to put a pension away. Okay, if you were setting up a state pension from scratch with today's life expectancy, the way the Lloyd George government did it, your pensionable life expectancy, you would get a pension at the age of about 90. Do you get the point? You can pick a pensionable age at anything you want. You know, what happened was that one was chosen because it was longer than life expectancy, but life expectancy has now lengthened, so everybody gets pension. Okay, and so there are questions around that, but they need to be totally uncoupled from biology. Or we could, if in an ideal world, you could go the other way and you could turn around and say, you know, you can retire when you're physiologically too old to work. I quite like that one, although I suspect I'd be trampled in the stampede. But, you know, because I must be honest, I felt too old to work for, oh God, at least 30 years. So I hope that provides a little bit. It is an interesting and it's a difficult thing when you get into the weeds, but you can kind of see where it's going. Okay, Anne, I think you had a question, didn't you? No, okay, fine, good. In which case, if nobody's got any others.
Would you mind if I ask one slightly?
No, not at all. Normally students ask me if this is on the exam, you see, so I'm always a bit flabbergasted when I don't get that.
Just one other little thing, those Maslow values, which were very fascinating. If one is aware of one Maslow's values, is awareness of them, if you're not happy with them, is there any mechanism to change them, or are you set with whatever you got?
That is a really profound question. I mean, let's put it this way. Knowing other people have different Maslow values certainly pulls the teeth on my "why are you such a pain in the backside" feeling. Now I know why you're a pain in the backside kind of thing. But don't forget, a Maslow value is based on an unmet need. So one cluster has to do with basically with security and belonging. It's the baseline human setting. I have, it's one of those odd things. I've actually been on a survival course to the Amazon. I did a bit of training beforehand, so I've been dumped in the Amazon on my own. And the moment you're in a survival situation with a small group of humans, i.e. duplicating 200,000 years of human history, you can understand why identity, security, and belonging are dominant human values, or dominant Maslow values for most of human history, because there's almost no food. You don't know what's out there. We're huddled round one fire, and there are things out there you don't want to meet, and some of those things look like us. Okay, that's identity, security, and belonging. Those kind of progression hierarchies are based on the fact that once you feel safe, you move on to another value. So it's that kind of thing. If you're a need which is met is no longer a need. But this boils down to two things. How big was your individual need? And how likely is it to be met? And so that is partly why I am fascinated by, I would really, really like to be able to do the genetics of Maslow values.
Yeah.
And so, yeah, people do change, you know, if they've got met needs. I mean, the classic one is the classic one that you see in kind of floating around in the sort of communications ether is when you move beyond the identity, security, and belonging kind of grouping, what is sometimes called the Maslow settlers. It's the first time where people have recognizable concepts of self-esteem. Okay, so you then enter what's known as a Maslow. A lot of people enter what's called a Maslow perspective phase, where I have no internally generated self-esteem. My goal is to get the things that will make you admire me. And those could be 3 strings of beads, some tiger teeth, you know, a Mercedes, a trophy wife, or a huge stack of money. What the thing is doesn't matter. It's what I think you will look at me carrying around and saying, my God, he's made it. And if that happens, the person starts to develop their own self-esteem and don't bother with things like that. And where you see this, you know, these kind of guys who've run a company where they've been busily putting absolutely everybody out of business, and bankrupting people and cheating widows and orphans, and then suddenly they'll have this great conversion and they'll open a cat's home. That's a Maslow, you know, that's a, I'm now a you know, I now realize what a great guy I am. That's a Maslow transition, and you can sometimes see it. Or somebody who feels sufficiently safe to say, my God, you know, I've got enough to eat, I've got enough to drink, I've got a roof over my head and a little bit of money. Is this all there is? Maybe I could be somebody, maybe I could make it. That's another kind of transition point. So they are interesting. Okay. Did I see that you do not look like Wendy Devonshire to me, sir, even in these strange times?
We are in strange times. I'd be interested in your thoughts of whether we would ever embrace the concept of a physiological age as opposed to a chronological age. Because it seems to me that people age at both ends of the age scale at different rates. And yet for bureaucratic reasons or whatever, you know, kids all go to school at 5, they all go on to secondary school at 11, yeah. Whether they're ready for it or not. And it's ditto with the other end of the
I couldn't sympathize with you more. I think that it would, I think what happens is this, like a lot of human society, the age categories that we use are a rough and ready kind of middle of the bell curve. You know, it captures most people that you've put in a bin. You know what it's like. I don't know. I guess we've all had kids, and if you're like me, you've obsessively bought what's the first year going to be like book. You know, I used to joke with my wife that we were a normal couple because our stack of parenting books was always shorter than our child. And you know, when you're a new parent, you're desperate. Oh my God, it's month 2 and he hasn't done this, but he has done this. And so, of course, what happens, I think, is we've organized things around kind of the top of the distribution where Mr. or Miss Average would be. And that means that there are people who are slower and people who are quicker. I think it would be nice if we could refine it. You know, I think we should try to do better with things like that. However, my experience of attempting to make what I think of as even quite rational policies tell me that it's a somewhat more, you know, I have tremendous respect for people who can manage to affect changes in policies and procedures. Because very briefly, I was a Royal Society science fellow for a while. So I was a parliamentary fellow for a little bit. And the mechanics of getting change through, however desirable, are, you know, not quite on a par with cracking human aging, but they're certainly not something you'd sit there and say, you know, oh well, that's a done deal. I'll just change the building regulations. So you know, yeah, it's a good idea. It's something we should drive towards, but you'll need a better man than me to put it in place. And that probably won't be difficult to find. But there we go.
One of the consequences, we have a sort of mentality of one size fits all, which will always have failures that are either extreme, which we just sort of abandon, if you like. But if we had more sophisticated, not one size fits all policies, we wouldn't have so many casualties, if you like. It's an interesting, I think there are 2 different things in play, and they tend to get conflated. That one, I think, is an important one, which is, you know, we go for one size fits all, but what we also go for that sits below the surface are radically conflicting ideas about what the thing we want to change is. So, I mean, a pension is a good case in point, yeah?
Is a pension something you've earned as a result of saving? Is it something to which you're entitled? You know, there are radically different ideas around how a pension is set up. They're all covered with pensions. My own favourite one, actually, returning to Maslow groups, because Maslow groups, unsurprisingly, have radically different ideas about what common institutions are for. If you look at the three main Maslow groups, you can call them prospectors, settlers, and pioneers, and you ask them what's the purpose of education. Settlers will tell you that the purpose of education is to equip you with the traditions and behaviors that will allow you to fit into our society. That's what it's for. It's to fit you into the group in a smooth way. All right. If you ask a Maslow prospector, the ones who get ahead, I've got no self-esteem, what the purpose of education is, it's to equip me with the skills that I need to trample on you. It's to allow me to compete effectively. Now, competing effectively is immediately incompatible with you being another person in lockstep. And if you ask the kind of, I've got my own self-esteem, Maslow pioneer group, they'll tell you that the purpose of education is to allow you to find yourself and to be all that you can be. At which point, the only thing that unites the settlers and prospectors is they're both staring at the pioneer, turning around and saying, what the hell is that person talking about? And our educational system is the result of the dynamic interaction of those three groups. And they comprise about a third of the population each. So when you've got confusion at the top about what an institution is supposed to deliver, when you combine it with a one-size-fits-all, you've got a difficult system to navigate. It can be done. I mean, you know, there is a whole interest in this, in how you change things. But the key thing actually that comes through very strongly, particularly if you do what I'm doing now, which is science communication, is a lot of scientists think that what they will do is they will throw a bunch of data at you, and you will then immediately see what has to be done. And the way in which I address this with my colleagues is I will sit and listen to, you know, I usually give them about 25 minutes, because that's you know, that's kind of, they've kind of run out of steam by then, where it's terrible and we need to do something, and haven't they seen the latest data on the mice, and what about Rapamycin, and what about senolytics, and this is all dreadful. And I turned around and said, supposing you go and see the Prime Minister, and after 5 minutes, he turns around and says, my God, I'm convinced the data are brilliant. You've got a blank check from me. What do you want? And so far, 9 out of 10 scientists that I've done this, and I've done this with a lot of them, have turned around and said, I never thought of that. Because they're that convinced, because that's how they think. Okay, and so the key thing with this is data doesn't get you positioned. You start from what you actually think about doing these things. I personally think physiologically based screens for stuff would be useful. It would blur the distinction between what we think of as retirement from ill health and retirement from premature old age, because we kind of do retire people from premature old age already, we just call it illness. But it would make a more holistic way of dealing with those things, but there are kind of bigger problems on the horizon. It's certainly a nice one for 8:30 on a Tuesday evening. What if, you know? Right.
Well, thanks very much, Richard.
That was lovely to meet you. Thank
Great,
you
yeah.
for being a terrifyingly interested audience. This is some of my colleagues are absolutely terrified of doing psychoms, because what tends to happen is you're used to watching the students nod approbation while they sleep, particularly on Zoom this year. Most of them are kind enough to turn their cameras off as well, so you feel like you're talking to a wall. But can you send us where, you know, when we want to send you the 30 million to fund the rest of the project, where do we send it? Into my bank account in the first instance, Mark. Perfect. If you could, I'll make sure it goes where it'll do the most good. All right. right. Do take care. Pleasure meeting you all.
Thank you
Okay,
very
I
much.
look forward to meeting you again. Take care.
Thank you.
Bye-bye.